Hi, my name is George Woodrow, and I'm giving a talk on creating fractal planets using Wolfram language. I've been using Mathematica since version 1.1, and I've given a couple talks before, and so there we go. I was watching Star Trek II, as you do when you have time, and I said, Jeepers Creepers, can I duplicate the Genesis planet flyby in Wolfram language? And I said, well, why not? And the abstract deadline was in July, so I figured I'd have plenty of time to get the whole thing done. Didn't quite work out that way. There are several documents that come with this. This notebook is the abridged 15-minute version. There's an expanded version, which has a lot of explanations, which I hope you can take a look at, and 2 or 3 data files. When I did this work, I was working with the Mathematica 12.1 beta, and it turned out that there were certain things that were fixed in 12.1 which were broken in 12.0 that I relied on. So we have a bit of, fooling around to get things to work here. Anyway, there's the thing. I've got Star Trek. I want to redo that. And then I looked at in the interwebs and found these videos by Lauren Carpenter, which I have on my hard drive if anyone is interested in taking a look at them. Interviews. Lauren Carpenter worked at Boeing at the time, I believe. He was one of the founders of Pixar, and he's a guy that invented fractal landscapes. So here's the background. This is a clip from the first fractal landscape made in 1980. And here's a clip from Star Trek II of the planet flyby. And what I wanted to do in this project was to implement a function to generate these fractal landscapes and to create a planet, which, as it turned out, they did not do in the code for Star Trek. And I wanted to make as much use of the built-in functionality in Wolfram language, at least for the initial explorations. Okay. The basic procedure is you start with a set of points. In the old code, which I had written an implementation for in the early 80s with my 128K Mac, the grids were kind of fixed. So you started with a fixed grid, you started at the corners, and you essentially have the step size each time. So I wanted to start with an arbitrary set of points, make a grid connecting them, and for each segment of the grid, then pick a new point halfway in between, and repeat until you have enough polygons to make something that looks convincing. The tricky bits are creating the grid and the code to select points. Creating a grid with arbitrary points is a non-trivial task, so I was looking for something built into Wolfram language that would take care of that for me. And the new Z values is a bit of an art, which I turned out was something I will still be working with. And I could have worked with flat maps and this wrapped that around the sphere, and that didn't work at all. So it turned out that the best way of proceeding was to deal with a sphere directly, which means spherical coordinates. Now, I never had spherical trigonometry in high school. My father did, which worked out very well for him because he was a navigator in B-29s in the war. And as it turned out that it was much easier for them to find pilots than it was to find navigators. And there were instances of not so swift navigators, and the planes never returned. So this was a really big deal at the time. And of course, by the time I was in high school, We had trigonometry, but not spherical trigonometry, and I have no idea what they're doing now, but I bet it's less, especially since you don't need to interpolate and you've got a calculator that they can give you. So we'll first go through the flat landscape, and then we'll go through essentially the same procedure again to do a planet on a sphere. Just making test data. Making a mesh, I found this wonderful function called Delaunay mesh, which you have random points and it makes a nice, pretty mesh for you. The problem is that if you give it three-dimensional coordinates, it will give you a three-dimensional mesh. There's no way in the built-in function to say, I want to have a two-ish dimensional surface embedded in 3 space. So what I did was I flattened the data by eliminating the z-coordinate, make the mesh using Delaunay mesh, extract the mesh lines using mesh primitives, and then restoring the z-coordinate. And in 2D, that was pretty good. And to make a new point, this is essentially I copied from the code from the 1980s because I figured, why not? Segment line, you find the Euclidean distance between the x and y coordinates. Pick a random number that in the range that depends on how big the segment is, and then apply some little sugar to make it smoother or flatter, bumpier. So as it turned out, if I use the Euclidean distance between the two actual points and not the points projected on the plane, the whole thing blew up. So the function that selects a new point is sensitive to what the conditions are, and this plays out later. So here's the function. It takes a list of data, which are the previous set of triples, and returns a new data set, which has the previous set plus the new ones. So the comments work pretty well. You take the Delaunay mesh by dropping the z-coordinate, which is the last one. Get the mesh lines by taking the mesh primitives. Make the lines from that, and then generate the new point, and then add them together. Everything's hunky-dory. And I'm not going to execute any of this code. We can make this a little bigger. But here's a sample grid, and that looks pretty good. Let's see if we can make that a little bigger here. I did not try to make this any fancier than necessary because all I wanted to do was to see whether the basic code worked. Okay. Come on. For the planet, we're going to do the same thing, except now we need to use spherical coordinates. And I had to look up, this is copied right from the documentation because, as pointed out in Math World, there's no standard way of notating spherical coordinates. Some of them have the r value first, some have them last, some have the theta value from the middle, some have it from the North Pole is here. So this I copied and kept with me so that I would not make a mistake when I was doing this work. Now, an important thing to look at here is that the theta value, which is essentially the distance from the North Pole, the angle from the North Pole, has to be greater than 0 or less than pi. And if that sounds great. If you're doing interactive work, and then you can say, well, fine, if I got the North Pole, then I know what to do. If you're doing thousands of computations, that's not working well. So what we ended up doing was to make a more robust function that wasn't perfect and that wasn't invertible, but it never failed. It always gave a triple of numbers. Initial values, it turns out, are more, it's more of an art than I thought, but I just use the vertices of a buckyball for my work here. Making the grid and extracting the lines, did exactly the same thing, except we used convex mesh hole instead of Delaunay mesh. Thing with a convex mesh hole is that you don't get all the points unless it's a sphere. So I did the same trick, flatten the surface to a surface of a sphere, get the primitives, and the same song and dance. Making a new point, I started working all kinds of fancy code, and then I remember I haven't had calculus in 45, 50 years. I remembered that if you have vectors and they're the same length, then the sum is another vector which bisects the angle. So I have a really nifty looking little, I should have made that a prettier size. Anyway, so to convince myself that my reasoning was right, I made this. And, okay, I forgot where I was. So here's basically the same code for making a new point on the planet. Same thing, you get, you find the new, okay, that's for finding the new point. Find the new radius, which is the average of the values. You get the angle between by doing the vector sum. And you can see here there's a lot of conversion back and forth between spherical and Cartesian coordinates, which back in the dark ages when I was writing was a really bad thing because trig functions are notoriously slow. Fortunately, our hardware is like 1,000,000 times faster, so we don't have to worry about that so much. So here's building the planet in one step. From structurally, it's exactly the same as building a landscape, except now you're using convex hole mesh instead of Delaunay mesh, and you're switching back and forth between Cartesian and spherical coordinates. So you transform the data to spherical coordinates, and then you do jumping back and forth. And this one I would really like to show you, except with 12.0 it fails when you try and make enough iterations to make it look interesting. So here's with one iteration, and I loaded in code which I had saved from 12.1. So this looks, decently planet-like, I think. Okay. And this was a primitive attempt at rendering the surfaces the way that Listplot 3D does, which doesn't work in spherical coordinates, I found out. Okay, so there we are. And in the expanded notebook, I show how to take an interesting section of thing, blow it up, flatten it, and then use an approximation to the plane, and then render this stuff. So here's a close-up view of that. So in principle, we've done. I haven't done the flyby stuff. There's a really nice Wolfram U course, half an hour presentation and a nice notebook on how to do camera angles and stuff like that. But in principle, we're done. I would have been more done, except I spent a whole lot of time trying to make the code work better. So it would be nice if we could leverage more of Wolfram's technology for relief plot and geo-elevation data. I don't know how well it's going to pan out. The problem that I had with the initial study was that if you try to work with a flat planet and then spherize it, you end up with issues at the North and South Pole, and of course you got that seam, which never worked out right, so I abandoned that. One of the issues we had with the random number generator is that the random seed doesn't do what you think it does if you're doing parallel processing. And I was told that if we use compiled functions, that'll work, and compiled functions should make this faster anyway. The issue with this segment length is something we really need to do, and I would really like to make a flyby. The really big thing was that we should actually make the proper mesh to begin with, instead of using the Delaunay mesh or the convex hull mesh. And I know that's possible because if you look at the list plot 3D, it's making a mesh on the fly of crinkly planar surfaces. So it's hidden in there, and if I figure if Wolfram guys can do it, I can do it, at least up to a point. And if possible, to eliminate the need to be shifting from spherical to Cartesian coordinates. So I'm going to close up the preamble. You can read that. Where's my, here we are. What's the point? Why did I do this? Okay, we don't do computation to get a number. We do it for insight. I don't remember who said this first, but it's all over the place. I was looking to see about learning some new maths. Now, clearly, spherical coordinates, spherical trigonometry is not new maths, but it's new to me. And I really need to understand meshes. I found this book on computational geometry that talks about that, so I got another 6 months or a year to work. The implementation and the starting points are critical. Now, I found an interview that Marcus Assoitoy had with Lauren Carpenter about 10 years ago about how he did this thing initially, and he said for his fractal landscapes, they carefully chose the initial points. If I had known that, then I wouldn't have just be picking things out at random. And this is even more true, I found, on trying to do a whole globe, because no matter what I did, you kind of detect the traces of a buckyball in the back there. The way of selecting new points is, from a mathematical sense, a bit of an art. But what we really want to do is we want to have a realistic landscape. And if you look at the fractal landscapes that are generated, and you can buy software that does it. I mean, you know, if you want something that looks really pretty, you don't use Wolfram language. You spend the $10 and buy the software. Is really good at emulating alpine scenes and mountains and stuff. It can't render something like the Bryce Canyon or the Grand Canyon for that. So at some point, we're going to need to make something that deals with actual geology. Now, you can make a fractal tree that's very realistic looking, and if you allow for the, you know, certain randomness in the lengths and stuff, you can make stuff looks right, because the model behind the fractal generator is exactly what real trees use. You know, trying to optimize the position of the branches so the leaves have the maximum sunlight and stuff. Geology doesn't work this way. If you think about it, the uplift part is very broadly based. I mean, if you have a plate crashing into another one, it's going to be pushing the other one up. So it's going to operate over a wide range. And erosion is local, so it's a much smaller range. So that's something else that I intend to be working on, simply because once you start, and it's not so obvious when you're just doing, say, a couple square miles or something, a surface or something to fly your Boeing airplane over, which is what was the genesis of the project 40 years ago. But if you want to build an actual planet, you're going to need to know something about plate tectonics and geology, and know that in the case of Bryce Canyon, for example, that different rocks erode differently. So you need to do that. So it's a bigger can of worms. And I think that in rendering that Pixar uses, they get around that by very carefully choosing their initial points. Okay, so oh, and the implementation in the back here, you can see everything that I did. All the relevant stuff is, I've already showed you. So, the other conclusion is, I've been writing code for quite a while, and as Amy Freeman said, Wolfram language is great for doing this kind of exploration type work. Really, the larger document that I provided is would be a basis of like a 40 or 50-minute talk. If I put in all the loose ends and false steps and stuff that I put in, it would like it'd be like a Stephen talk. Probably a little bit less interesting, but more illuminating, especially if you're trying to teach a student or something how to program or how to discover things about mathematics of the world. It's much easier to do that than to write even in a modern language like Python or Swift, where you have to worry about computer sciencey stuff all the time. And as now that we have the Wolfram Alpha Notebook Edition, we should probably try to see how it would work in that. Okay, so that's my talk. If anyone's interested, I'm going to be putting further versions of this up in the Wolfram community or publish it to the web now that we can do that. And any comments or stuff, everyone should know how to find me because my email address is all over. Okay, thanks.